Hello everyone, welcome to the fourth class of this course. So in the last class we saw whether so if we are given a differential equation and we are asked to find out uh, a series solution around some point, let's say x naught, whether at all we can find a solution or not. So those things are characterized by ordinary points, regular singular points, and essential singular points. So in this class uh, we will try to solve some differential equations uh, around some ordinary points, So let's take example 1. Example 1. Okay. So the differential equation is basically y double dash equals to x times y. Okay. Or we can write it as y double dash minus x times y equals to 0. Or we can also write it as y double dash minus plus 0 times y dash minus x times y equals to 0. Okay, let me complete the question first. So here you are given this differential equation and we are asked to find out. So find out series solution at x equals to 0. So around 0 we are asked to find out the series solution if the solution at all exists, if the solution exists. Okay, so first of all we need to check whether x equals to 0 is an ordinary point or an regular singular point. So in those cases we can get a power series solution. Okay, so as this today's topic suggests, so we will be solving around ordinary points, and you will see that okay, x equals to 0 is an ordinary point for this differential equation. So here what is this px? Px is the coefficient of y double dash, which is 1, right? This qx is the coefficient of y dash, which is 0, and rx is minus x, right? And it's very easy to see, like qx by px at x equals to 0 equals to 0, and rx by px at x equals to 0 equals to 0, or rather I can just say that this px at x equals to 0 equals to 1, or it is always 1. So it means qx by px and rx by px both are analytic at x equals to 0. So that means x equals to 0 point, it's an ordinary point. Okay, so the power series solution exists, and the solution, so let's assume the solution is basically yx equals to sum over n equals to 0 to infinity a n x minus x naught to the power n, and here x naught is 0, so that means I can write it as x to the power n. Okay, and now our job is to find out these ans. Okay, so this y we already have, right? Okay, so what we have is basically yx equals to this, so that means y dash x will be n equals to 0 to infinity in an x to the power n minus 1, right? Or n equals to 1 to infinity, because if I put n equals to 0, then this term is 0. So basically n starting from 0 or n starting from 1 is basically same thing, because the 0th term in this series, the 0th term is 0 because of this n's here, because of this n here. Okay, so it is n an x to the power n minus 1, and if I take y double, if I calculate y double dash x, then it will be sum over n equals to 1 to infinity n times n minus 1 an x to the power n minus 2. Okay, that's the simple ddx of that. And here I can write it also as n equals to 2 to infinity, because if I put n equals to 1, so n equals to 1th term, so if I put here, then this term is 0. So basically n equals to 1, n equals, if I put n equals to 1, then that term is basically 0, so I can start from n equals to 2. Fine. And so this is the first term of the given differential equation. Okay, so this term, the other term is x times y, x times y. So the other term is x times y. Okay, let me take care of that term a little bit later. So let me first look at this term, y double dash equals to sum over n equals to 2 to infinity n times n minus 1 at an x to the power n minus 2. Here x has a power of n minus 2, and we want to compare the powers. So we don't want x having power n minus 2, we want this kind of terms, like we want something n equals to something and we want x to the power n. Okay, so in that case we can compare the powers. So the requirement will be much more clearer once if I put them in the differential equation. So for the time being, let's assume n minus 2 equals to m. Okay, so in that case n equals to m plus 2, and if n equals to 2, then m equals to 0, and n tends to infinity means m also tends to infinity. So in that case y double dash x, if I replace this n by m, so then the summation, it was starting from n equals to 2, now it will, so n equals to 2 means m equals to 0, so I can write it as m equals to 0 to infinity, right? And instead of n I will write m plus 2, so it will be m plus 2, and if I put m plus 2 here, it will be m plus 1, because there is a minus 1 sitting here, it will be m plus 1 times a m plus 2, right? Instead of n I am putting m plus 2, this. Okay, and x to the power m. And now I can replace this m by n because it's a summation index. So n plus 1 n plus 2. I'm just interchanging these two terms. Okay, I'm writing this one first, and then this one. 2an plus 2 x to the power n. And now, so this is the first term of this differential equation. Now this term, second term, which is x times y. So x times y, and y we know that y is this sum over n x to the power n. So it will be then x times sum over n equals to 0 to infinity an x to the power n, which is nothing but n equals to 0 to infinity an x to the power n plus 1. You can try to solve it along with me. In that case, the class will not be boring. Okay, so here also you can see x has a power of n plus 1, but we don't want that. We want x to have a power of x to the power n, for easy comparison. In that case, here I will assume that n plus 1 equals to, let's say, p. In that case, n equals to p minus 1, right? And n equals to 0, it means p equals to 1, and n equals to n tends to infinity. Sorry. N tends to infinity implies p tends to infinity. Okay, and if I do that, then what we have is basically p equals to n equals to 0 means p equals to 1. So p equals to 1 to infinity a of p minus 1 x to the power p, or as p is a summation index, I can just replace p by n. So n equals to 1 to infinity a to the power n minus 1 x to the power n. Okay, and now if I will put these two terms, this term and this term, in the given differential equation, which is y double dash equals to xy. Okay, so the given differential equation is y double dash minus xy equals to 0, which implies y double dash is n equals to 0 to infinity n plus 1 times n minus n plus 2, n plus 1 times n plus 2 times a n plus 2, right? A n plus 2 x to the power n minus this term xy is n equals to 1 to infinity a n minus 1 x to the power n equals to 0. Okay, still now we cannot compare the power, though both are in x to the power and x to the power n. But here you can see this series, the first one, it starts from n equals to 0 and it starts from n equals to 1. Okay, so what I can do in this case is n equals to 0th term I can write it separately. Okay, so this series I can write as, this whole series, this I can write as, I will write first the n equals to 0th term, which is, so I will put n equals to 0 here, that means 1 times 2, which is 2. If I put n equals to 0 here, it is a2, so it is a2, and if I put n equals to 0 here, this is just nothing but 1, x to the power 0 is 1. Okay, this is the first term of this series, and from the second term I can write as the summation, that is n equals to 1 to infinity n plus 1 n plus 2 a n plus 2 x to the power n minus this other series, which is n equals to 1 to infinity a n minus 1 x to the power n equals to 0. Okay, so this two terms is basically this series n equals to 0 to infinity, and here I am writing the 0th term separately and writing the all other term in a series summation. And the last term the last series I am keeping as it is. This series is basically this one. Fine. And now let's see, you can see these two series, this series and this series, both have x to the power n and both are starting from n equals to 1. Now we can bring them together and we can write it as n equals to 1 to infinity. We can take x to the power n common and we can write n plus 1, n plus 2, a n plus 2 minus a n minus 1, equals to 0. Okay. And from here we can write, so from here we can see that we can write that all the coefficients will be 0, right? This is because of let's say if sum over lambda I x to the power I equals to 0 to infinity equals to 0, it implies all the lambda i's are 0, right? So using that I can write a2 equals to 0 because this is a constant term, and other will be coefficient of this x to the power 1, x to the power 2, dot dot dot. So in that case I can write it as n plus 1. So this is 1, and then n plus 2, a n plus 2 minus a n minus 1. So this is the coefficient of x to the power n, where n is 1, 2, 3, 4, 5, 6. N is not equals to 0. The 0th term is taken care here. Okay, so equals to 0, or I can write it as a n plus 2. Let me give a little bit of a gap. Okay, so a n plus 2 equals to a n minus 1 divided by n plus 1 n plus 2. This is the, let me call it equation 1. Okay, and this is our recurrence relation. So if I know n minus 1th term, I can get n plus 2th term. Okay, and we know a2 equals to 0. So let's see what this recurrence relation does. Let me write an n axis. Okay, let me start with so this is the I. So let's say this is the ith term. So let's say this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10. Okay, 0, the 0th term. So 0 corresponds to a0. Okay, so let me write it like this. Let's say a0, a1, a2, a3, a4, a5, A6, A7, A8, A9, A10, dot 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 dot. Okay. So our goal is to find these A's, A1, A2, A3, A4, A5, AN basically. That was our goal. So these coefficients we need to find. So let's see what this recurrence relation does. Let's assume that, okay, I know A0. So in that case, if I know A0, so from this recurrence relation, if I put n equals to 1, okay, so then what this term will give? So let's say, for example, let's say I know A0. Okay. And in this recurrence relation, if I put n equals to 1, if I put n equals to 1 in this recurrence relation, what it will give? It will give you this will be A0 then. So and here it will give me A3 if I put n equals to 1. So from the recurrence relation I can see it is A3 equals to A0 divided by n equals to 1, so it will be 2 times 3, or I can write it 3 times 2. Good. So what it is doing is basically, if I know A0, I can find out A3. Now if I know A3, for example, I know A3, in that case, so here in the recurrence relation, so this term will give me A3 if I put n equals to 4, right? If I put n equals to 4, then it will be A3. So if I put n equals to 4, so then this term will be A6, right? So A6 equals to, this term is A3 divided by 4 plus 1, that is 5, and 4 plus 2, 6, right? So 6 times 5, or rather write it as like this, 2 times 3, and 5 times 6. Okay, so n equals to 4, that means this is 5, this is 6. So 5 times 6, and now I know what is I know what is A3. So in that case, I can write it as A0, or write it here. If I put A3 from here, I can write it as A0 divided by 2 times 3 times 5 times 6. Okay. Similarly, so if I know A3 now, if I have A3, so from A0 I found A3, and then what I did is from A3 I got A6. Okay, so here from A3 I got A6. On the other hand, let's say we know A1. Okay, let's say we know A1. So in that case, if I put here n equals to 2 in this recurrence relation, if I put n equals to 2, so in that case what we can see is basically A4, so n equals to 2, that means A4 equals to A1, so n equals to 2, that means n minus 1 is 1, so A1 divided by 3, n plus 1 is 3 because n equals to 2, and n plus 2 is 4. Okay, so this is 3 times 4. So if I know A1, then I can find A4. That's the job of recurrence relation. So if I know A1, then I can find A4. Similarly, if I know A4, you will see, if I know A4, then we can find A7. So in that case, I need to put n equals to 5 here. Okay, so if I put n equals to 5 in the reconciliation, what it will give, the first term is a7, right? N equals to 5, that means this is a7 equals to, so n equals to 5. Okay, so that means this is a4, divided by 6 times 7, right? 6.7. so n plus 1 is 6 because n equals to 5, and n plus 2 is 7, and we know what is a4, so then we can write it as a1 divided by 3 times 4 times 6 times 7, and this is how we can proceed. This is how we can proceed. Okay. And a2 we already know, a2 equals to 0. Okay, so in that case here, okay, a2 equals to 0 you already know. So here to go from n equals to 0 to n equals to 3, so to go from a0 to a3, what we did is we put n equals to 1. We put n equals to 1. To go from a3 to a6, we put n equals to 4. Okay, here we put n equals to 2, and here we put n equals to 5, right? Now, for example, I know someone claims that, okay, I know a2, then where I can go using this reconciliation? So if I put n equals to 3 in this case, then you can see that this term will be a2, and this term will be a5 if I put n equals to 3. So if I put n equals to 3, then I can go from a2 to a5. Similarly, I can go from a5 to a8 by putting n equals to 6, right? But we know that a2 equals to 0. That means a5, a8, these terms, like a2 equals to 0, and a5 will be something multiplied with a2, right? Using if I follow the recurrence relation, that means a5 will also be 0. Similarly, a8 will be something multiplied with a5, and a5 will is 0 because a2 is 0, and as a result a8 is also 0. So in this way, these terms like a8, and then this will be a11, right? So these terms will be 0, and these terms like a0, a3, a6, similarly a9, a10, these terms will be surviving. So what we got, basically two series. One is this green one, that is we will start with a0 and then follow the recurrence relation, and other is the blue one, that is we start with a1. So so this is a0, okay, and this is a1. So we start with a1 and then we will follow the recurrence relation. These are the two series we got. Okay, so if I follow the recurrence relation, it's basically what you can see from here. The general term is basically a of 3k equals to a0 2 times 3 times 5 times 6 ... 3k minus 1 times 3k for k equals to 1, 2 ... 3 ... This is the a0 series, like if I proceed from a0 and follow the recurrence relation. Okay, so following this pattern I am writing this kth term basically, and here the kth term will be, so it will be like k plus 1th term, so it is a6 and a7, so it will be like a of 3k plus 1, and it will be a1 divided by 3 4 dot 6 7 dot 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 multiplied with 3k times 3k plus 1, right? The last term is a7, and this multiplication factor is 7, so it is 3k plus 1 if this term is characterized by 3k plus 1. So the last term here it will be 3k plus 1. Okay, so these are the two series we got, and from a2 if we proceed, so a2 is 0 from this equation 1, and that means this a5 a8 like 3k plus 2th term, those will be 0. So the general solution I can write it as yx equals to a0 plus a1 x plus a2 x square plus a3 x cube plus a4 x4 plus a5 x to the power 5 okay, plus a6 x to the power 6 plus a7 x to the power 7 plus a8 x to the power 8 plus dot dot dot. Okay, and now what we know is basically this a2 is 0, this a5 is 0, this a8 is 0. Okay, and this a0, okay, this a0, from a0 if I start, then this term will follow. So from a0 I will get a3, I will get a6, and from a1 I will get, if I start from a1 I will get a4, I will get a7 and other terms. So I can write it as in terms of two series. One is one which starts from a0 and which will contain only the term, only the ai's which are in in multiplication with a0. That means the a3, a3 x cube plus a6 x to the power 6 plus dot dot dot. This will be one series, and the other one will be starting from a1x plus a4 x to the power 4 plus a7 x to the power 7 plus dot dot dot. Okay, so this will be the solution, or it can also be written as, if I take a0 common, then it will be 1 plus, so this term will be from, let's say, k equals to 1 to infinity, okay, x to the power 3k, and to the kth, 3kth term is basically 2 3 5 6, so 2 3 times 5 times 6 times dot 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 times 3k minus 1 times 3k, right? So this will be the series of a0, the first series, and the second series will be a1 times x plus k equals to 1 to infinity x to the power 3k plus 1 3 times 4 times 6 times 7 times dot 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 3k times 3k plus 1. So these will be the two series, like, so these will be the two solutions. This is, for example, you can write y0 of x, and this is the green one, right? This we can write it as y0 of x. This is the first series solution, and this we can write it as y1 of x, and the general solution will be yx, which is a0 times y0 of x plus a1 times y1 of x. So this is the general solution. So as it's a second order differential equation, so we are basically getting two linearly independent solutions, and the general solution will be a linear combination of them, these two linearly independent solutions are these two power series. Okay, so this y0 and this y1. This is how we can find a power series solution at some ordinary point. Okay, so that's one example for this class. In the next class I will do another example, and then I will take some examples from Frobenius method, that is for regular singular points. Okay, so that's all for today. Bye.